Hello students, next we will start with the inverse discrete time Fourier transform, also known as IDTFT, or sometimes just called as inverse Fourier transform. The basic equation of inverse DTFT is already discussed. I will once again write it. That means that the Fourier inverse of x of omega will give us the sequence x of n from this particular equation. But this is not the equation that we will always use to find out the inverse DTFT. We can find out inverse DTFT using some other methods. Let us see one by one with the help of examples. Before that, let us look at some of the equations that are useful for us for solving the inverse DTFT. These are the series expansion equation. The first one is 1 by 1 minus x, which can also be written as 1 minus x inverse, which can be found out by using the formula 1 plus x square plus x cube, like that all the way up to infinity. The second one is 1 by 1 plus x or 1 plus x inverse, and its equation is also simple: 1 minus x plus x square minus x cube plus x raised to power 4 minus x raised to power 5, like that. So alternate values become negative here. Then the third one we are having is the square of this. That means 1 divided by 1 minus x the whole square. This can be even written as 1 minus x the whole raised to power minus 2, which is 1 plus 2x plus 3x square plus 4x cube, like that the series will go forward. Similarly, if we are having the square of 1 plus x term, that means 1 divided by 1 plus x the whole square, which can be written as 1 plus x the whole raised to power minus 2. That, following from our above example, 1 minus 2x plus 3x square minus 4x cube plus, like that it will keep on going. And next is the fifth one, which comes out to be 1 divided by 1 minus x into 1 plus x, which is also sometimes written as 1 divided by 1 square minus x square, or 1 minus x square, which is also sometimes written as 1 minus x square the whole raised to power minus 1, which is written as 1 plus x square plus x raised to power 4 plus x raised to power 6. That means only even powers. Okay, the next one in this series is e raised to power x, which can be written as 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial, like that up to infinity. Similarly, the next one I can write it as log 1 plus x is equal to x minus x square by 2 plus x cube by 3 minus, like that it will keep on going. Obviously, if the magnitude of x is less than 1. Now what you must remember is that in all these series expansion equations, we are considering that the magnitude of x is less than 1. Okay, should not forget that. Next, let us start with some of the simple examples of inverse DTFT. So find the inverse DTFT for the first order recursive filter. Now you might be thinking, where has this first order recursive filter all of a sudden come from? Don't look at that. Just look at that it's some filter which is having a transfer function h of omega is equal to 1 minus a e raised to power j omega raised to power minus 1. Now I can very simply write that h of omega is 1 divided by 1 minus a e raised to power j omega, from which if you would try to take the inverse discrete Fourier transform, we have already seen that u of a raised to power n, u of n is going to be 1 divided by 1 minus a e raised to power j omega. I can very easily write that, but I am trying to use a different solution here. So what I will try to do is, I will first write h of omega is equal to 1 minus a e raised to power j omega raised to power minus 1. Now using the series expansion, which is the series expansion that we are talking about? We are talking about the series expansion that we had just now seen, 1 minus x the whole raised to power minus 1. Okay, what was that? 1 plus x square plus x cube plus like that. So based on that, I can therefore write h of omega is equal to, if I am going to expand it, then I will get 1 plus a e raised to power j omega plus a square e raised to power j omega square, which is j twice omega. So I will write omega 2 instead of omega 2, I will write j twice of omega plus a cube e raised to power j thrice of omega. Like that, using the series expansion, I have written it like this. Next, I will write the equation of discrete time Fourier transform. So I will write, we know Dtft of x of n is, what is the equation of Dtft of x of n? We know that the Dtft of x of n, which is given by summation n is equal to minus infinity to infinity, okay, x of n e raised to power minus j omega n. Now here, since we are dealing with h of omega, I will write, instead of x, I will write h of n. So h of n e raised to power, what is this? So if I am going to write for equation all the way from negative values, then from some minus infinity, let me say that I am talking about h of minus 2, that means n is equal to minus 2, e raised to power j twice omega, correct, plus h of minus 3 e raised to power plus j omega j 3 omega. Sorry, I should have gone down, no? So this is minus 1, sorry. So this will be h of minus 1 is equal to j of omega, then h of 0 e raised to power 0, which is going to be just 1. So I will just write h of 0 plus h1 e raised to power minus j omega plus h2 e raised to power minus j2 omega plus, like that it will keep on going. Now if I am trying to compare both these equations, that I am trying to compare this equation with this equation, then what do you see? We see that since this is existing from 1 and j omega, twice omega, 3 omega, that is actually meeting here. You can see this from starting from h of 0, then here e raised to power j omega is there, here e raised to power j twice omega is there, then after that 3 times omega will come. So what we can see is that from here I can basically say, so comparing the two equations, what do I get? I will get h of 0 is same as 1. So I will get h of 0 is equal to 1. Similarly, h of minus 1 is equal to, how much is h of minus 1? A. Then h of minus 2 is equal to a square. Similarly, h of minus 3 is equal to a raised to power 3. Like that it will keep on going, isn't it? Which if I would write h of n if I would write, then it is starting from h of 0, which is 1, then a square, then a cube, like that it is going all the way up to infinity, and this is where I will put the arrow, because that is h of 0, isn't it? Which actually can be written as u of I will write this as, you can look here, a raised to power minus n u of minus n, a raised to power minus n u of minus n. Correct? You can put the values of n here, you will see that you will get exactly this value. Correct? So based on that, now we have, let us have a look whether it is correct. Yes. Therefore I can say that 1 minus a e raised to power j omega, which is basically what was our h of omega inverse, which is basically our h of omega. The Fourier transform of that, the inverse Fourier transform of that, okay, is going to be, so I will write here IDTFT. Sometimes in some cases it is also just simply written as Fourier inverse as F inverse. Okay, so the Fourier inverse of that is going to be h of n is a raised to power minus n u of minus n. Okay, clear? Now you can check for now similarly you can try on your own. To find that 1 minus a e raised to power minus j omega inverse will have a Fourier inverse of a raised to power n u of n. Okay, so you can check that, try on your own. So here we have completed this much. Okay, next problem, find the output sequence y of n from the output spectrum, which is given by this equation. Okay, so we have been given the output y of omega, from which we have to find out y of n. Now we know that y of n is basically the Fourier inverse of this whole expression, which is 1 by 4 e raised to power j2 omega plus 1 plus e raised to power minus j2 omega the whole divided by 1 minus a e raised to power minus j omega. Now it might look like a very complex equation, but we need not worry. We can basically, split this into many smaller components by, you can have a look. See, keeping the denominator common, I can write this as one equation. Okay. Similarly, this can be written as another equation, and similarly the third one can be written as another equation. So I will write all three of this separately and try to find out the Fourier inverse of that, because from the property of linearity we can do that. Therefore, writing afresh, I will write y of n will be obtained. I will take 1 by 4 common because that is a constant, so I can take that out. Then I will have Fourier inverse of the first component, which was e raised to power j twice omega divided by 1 minus a e raised to power minus j omega. Okay. Next is Fourier inverse of the central portion, which is 1 divided by 1 minus a e raised to power minus j omega. And the third is Fourier inverse of e raised to power minus j twice omega divided by 1 minus a e raised to power minus j omega. Okay. Now we know, so I will use this, we know that 1 divided by 1 minus a e raised to power minus j omega can be written as a raised to power n u of n. Okay, we have already seen that. And we use the time shifting property. What is the time shifting property says? The time shifting property basically says that if you are having a signal x of n whose Fourier transform you already know is x of omega, then for finding out the Fourier transform of x of n plus n naught, all you have to do is multiply it with e raised to power j omega n naught. Okay, so what you can see here is this is the extra multiplication that has taken place. This one directly we can write it using this particular formula, and for these two cases we can write that this particular function is multiplied with e raised to power j2 omega, so that will mean that it is a time shifting case. Therefore, I will write now, therefore y of n is 1 by 4. Now this is basically using the property a raised to power n, and since this is plus 2 omega, so I will write plus 2 a raised to power n plus 2 u of n plus 2. The central portion will be a raised to power n u of n. The last portion, the third portion, will be, since it is e raised to power minus j omega 2, I will write this as a raised to power n minus 2 u of n minus 2. Okay, so this is how we have found out the Fourier inverse spectrum in this particular case. So as you can see, the first instant we did a simple comparison, and the second instance we did a, we used the property. Next, the impulse response of an LTI system is h of n, which is given. Find the response of the system for the input x of n. We know that if you want to find y of n, we know if we want to find y of n, it is basically the input convoluted with the or convolution sum with the system h of n. And we know generally how to do that, but here we are going to use the Fourier transform method. So here I will write using Fourier transform method. So we are going to use the Fourier transform method. So what is the Fourier transform method says? See, let me try to explain it here. Generally we say that if we are having a system h of n, and if there is an input to it which is x of n, we can find out the output y of n by taking the convolution of x of n with h of n. Okay, if that is the case, from the Fourier transform or discrete time Fourier transform, we know the same thing is going to be like, we are having instead of x of n, we will take the Fourier transform of x of n, which is capital X of omega. That is going to be given as an input to h of n, whose Fourier transform is h of omega. Okay, whose Fourier transform is h of omega, whose output is capital Y of omega. Okay, and what is the equation of capital Y of omega? It is simply x of omega multiplied with h of omega. So this conversion, that convolution in time domain, gets converted to multiplication in frequency domain, actually helps us to find out the value of either y omega or the value of any of the unknown. That means if I am going to look at this equation, I can automatically say that h of omega is going to be equal to y of omega divided by x of omega. Correct? So if we are given output and the system, you can find out what is the x of omega. Or if that is not the case, if you are just given the output and the input, that means if you are given both these values, you can find h of omega using this equation. Or as it is done here, if you are given x of omega and h of omega, you can find y of omega. Now whatever be the case, if you know any one of these, that means you either if you know two of these, that means you either know h of omega, x of omega, or y of omega. Any two of these if you know, you can find out the third one. Now if the third one is h of omega, then you can take the Fourier inverse transform to get h of n. If the third one that you wanted to find was x of omega and you found out x of omega, from there you take the inverse discrete Fourier transform, you will get x of n. Similarly, if you have found out what is y of omega and you want to find out y of n, all you have to do is the inverse Fourier transform to basically find out y of n. So all these cases you basically use Fourier inverse transform. Okay, Fourier inverse transform, and this is basically one of the advantages of using Fourier transform. Though in the next module you will study Z transform, which is much better than the Fourier transform, but similar conditions, similar equations can be used in the Fourier transform also to find out the answers. So here what we have been given is, we have been given h of n, x of n. We know that if h of n, x of n is given, then we can find out h of omega, x of omega. Multiply both of those, you will get y of omega. If you get y of omega, in the end you take the Fourier inverse of y of omega, you will get y of n. So one way of getting y of n is convolution like this. The second method is by using this method. So we will solve this problem using the Fourier transform technique. Therefore we first start finding h of omega. Okay, or we can start finding the x of omega first, that is the input. Therefore x of omega, we know the equation summation n is equal to minus infinity to infinity x of n e raised to power minus j omega n, and h is basically, you know, having the first value at h of x is having the first value. Since there is no arrow drawn here, we will assume that the arrow is in the first. Similarly here also the arrow will be in the first. So this is your x of 0. So basically it is starting, I will write this as x of 0 e raised to power 0, which is 1, plus x of 1 e raised to power j omega minus j omega, plus x of 2 e raised to power minus j twice omega, plus x of 3 e raised to power minus j 3 omega, e raised to power minus j 3 omega, plus x of 3 e raised to power minus j 3 omega. Okay, therefore x of omega, by putting the value of x of 0, which is 1 plus 3 e raised to power minus j omega, plus 2 e raised to power minus j 2 omega, plus 3, which is 1 into e raised to power minus j 3 omega, which I will simply write it as e raised to power minus j 3 omega. Okay, now similarly I will find out h of omega, and capital H of omega is going to be summation n is equal to minus infinity to infinity h of n e raised to power minus j omega n. Now instead of expanding, I will straight away write, because it is starting from n is equal to 0. So first is 1, 2, 1 minus 2. So I will write 1, 2 e raised to power minus j omega minus, the next value is, not minus, plus 1 e raised to power minus j twice of omega minus 2 e raised to power minus j 3 omega. Okay, therefore what we will do is, we can find out y of omega, which is equal to x of omega into h of omega. Now if I am going to multiply, I will first start with 1 into the whole, which is 1 plus 2 e raised to power minus j omega plus e raised to power minus j 2 omega minus 2 e raised to power minus j 3 omega. Okay, next is 3 times, the next is 3 times this, so plus 3 e raised to power minus j omega plus 6. Okay, plus 6, it is multiplication, 3 into 2 is 6, which I am multiplying with this, with each one of those. Okay, so the second one is 3 into 2 6 e raised to power minus j twice omega, plus the next one is 3 e raised to power minus j 3 omega, and the next one is minus 6 e raised to power minus j 4 omega. Okay, the next one is with 2, so plus 2 e raised to power minus j 2 omega, then plus 4 e raised to power minus j 3 omega, plus 2 e raised to power minus j 4 omega. The last one is minus 4 e raised to power minus j 5 omega. Okay, and similarly I can write for the last one, then the last one is going to be e raised to power plus e raised to power minus j omega 3 omega, j3 omega plus 2 times e raised to power minus j4 omega plus e raised to power minus j5 omega minus 2 e raised to power minus j6 omega. So you should remember e raised to power a into e raised to power b is e raised to power a plus b. That is what we have used. Okay, so based on that I have got this equation. Now you can see that there are multiple, for example, e raised to power j3 omega is coming here, it is coming here, similarly it is coming here. So I can add all of these e raised to power j3 omega terms, even this one. So you can see this is minus 2 plus 3 which is 1 plus 4 which is 5 plus 1 which is 6. So I can write e raised to power minus j3 omega has a value of 6 when you add all of them up. So by adding all of them up, what I will get is, therefore y of omega is equal to 1 plus 5 e raised to power minus j omega plus 9 e raised to power minus j twice omega plus, just now we had calculated, 6 times e raised to power minus j3 omega. So 3 omega has a value of 6. Okay, minus 2 e raised to power minus j4 omega minus 3 e raised to power minus j5 omega, and finally minus 2 e raised to power minus j6 omega. Okay, so this is y omega value. Now to find out y of n, we have to take, so y of n is basically the Fourier inverse of y of omega. So if you I have to write like this, okay, y of omega. So if you take the Fourier inverse, you will get y of n. So to take the Fourier inverse, I have to just take the individual. So using just two things, using the fact that 1 gives me delta n gives me a Fourier transform or DTFT of 1, and e raised to power j omega n naught, delta n minus n naught, delta n minus n naught, which is basically time shifting, is going to give me a Fourier transform of e raised to power minus j omega n naught into 1. Okay, and since if I am going to write some capital A here also a multiplication factor of capital A will come. Therefore I can take the individual Fourier transform of each of them. Individual. I will be using this Fourier inverse transform. So all I have to do is therefore taking Fourier inverse of y of omega, what will I get? I will get y of n, which is equal to, so one is going to be delta n, the second one is plus 5 e raised to power minus j omega. What is the value of n naught here? N naught is equal to 1, so delta n minus 1 plus 9 delta n minus 2 plus 6 delta n minus 3 minus 2 delta n minus 4 minus 3 delta delta n minus 5, and finally minus 2 delta n minus 6. Okay, which now I can write it as y of n is equal to, now I'll put the bracket and I'll put each of these values, isn't it? So it is 1 comma 5 comma 9 comma 6 comma minus 2 comma minus 3 comma minus 2. So that is how we find out bi of n using the Fourier transform technique.